So today's lab was about text analysis and entity resolution. Sorry, let me see if I have the right one. Yeah, this is the one. So let's close this. And yeah, here we are. So the idea here is that often happens in data problems that you have records that you maybe want to identify as unique records. And what happens sometimes is that, sorry, one second. I think I hear a lot of noise. So I'm going to try to mute. Okay. So there was some background noise. I just muted it. All right. So what happens sometimes is that you have records that you think they are different from each other, but there are some cases where that is not the case. So what you would have to do is find ways to identify some sort of similarity between the records, and then from that decide whether those two records are actually different records. So in a way, it's the duplication of records. What happens is, of course, there is no correct matching. If there was correct matching, they would be straightforward. And in the case of RDDs, there are some functions that we covered last week to remove duplicates. But if what happens is that there is not an exact match, you would have to find ways around it. So typically, what you would do is you could compare in principle one match to the next. But that would be very expensive, and in fact, that's what the first part of the lab does: comparing each record to all the records available. But if you think about it, you would have to do a lot of comparisons, and that could quickly go out of hand. So there are some ways to simplify, or at least do some approximate matching, and then from that, you can reduce the number of comparisons, and of course the computational resources that you would use. And so in this lab, although in the previous week we did all of our work in data frames, here we go back to RDDs, but keep in mind that sort of the methods that you learn in RDDs, or once you understand how things work in RDD, you can easily translate that to data frames. But for this exercise, all the lab was just designed in RDDs. So the two records that we have is the record of a product. So there are two, one from Amazon, one from Google. And the format of it is CSV. So you would have the following columns: ID, title, description, manufacturer, price. And then on the other would have the Google would have ID, name, description, manufacturer, and price. And in this case, we do have a gold standard, and what that means is that we have a way. We have the true matching of records. There would be cases where you would not necessarily have that. Cases where the matching might not be, or the true value, the ground truth might not be provided. So you would have, what you would have to do is sort of examine those records for which the similarity is very high. And if that is the case, if the similarity is high, then you would examine those and then see whether whatever algorithm you're doing is doing what it's supposed to do, or if there are parameters in the algorithm. For instance, you do a particular cut in, say, some sort of similarity measurement, you would adjust the threshold by examining your data. But in this case, we do have the ground truth, so that is advantageous. All this, the first part where you do the parsing of you do the parsing of the data set is done for you. So nothing really to develop there. And I'm just gonna skip it, at least unless somebody has a question particular to the parsing. But I mean, this is the sort of thing that we've done before. You create a parsing function that just applies directly into the RDD. So this particular function receives a file name and reads that one file name. So not much to do there. So if we run that, what we can do instead is sort of examine that those files and see they actually match what we said it was going to be. So there's the two type of records. There's the Google record and the Amazon record, and then we each one of them would have different identifiers. So for the Amazon would have some unique identifier, and for the Google also would be a unique identifier, but in this case it's in the form of a URL. And then in this case there were other fields, but we extracted only the unique identifier and the description. Notice that in this case we ignored the price. You could in principle use that information to improve the model. If you notice, for instance, if you have a feeling that in both databases would have some sort of similar record, in this case let's say the price, you could use that to further decide whether two items are the same or at least they're similar. But in this case, sort of doing the baseline, we just stayed with the description. So in principle, the hypothesis here is the description in both places should be similar. And how do you go about it? Notice that what we have is text associated with each one of those items. So there is a method called bag of words, and what it does is you would create a set of all the words of this particular record and put them in a bag. What that means is that the order doesn't matter. So if you would have the exact same test just scramble, it would have the exact same mapping, right? So you're in a way ignoring the order and the semantics of the text itself. And then what you would do is try to compare how many times a particular word appears in the description of item A versus the same sort of words that would happen in item B. And then in principle, if there is an overlap between those two, then you could say that those two are similar with each other. Any questions until here before we get started into the actual algorithmic part? Do we have Eyal today?
Yes, I do. I'm here, Armando.
Okay, good to hear. That's good to hear. All right, no questions until there. Thank you, Eyal, for participating. Your contributions are always welcome. If there are no words, let's just go on with the lab. So the very first step is to tokenize that string, so that description that we found. And then, so if you want to split it, you could use the function split. So this is from the regular expression library. Well, I think there is a question on the chat. There is no sound. Oh, there is no sound. How about now? Can you hear me? Can people hear me?
Yeah, we can hear you fine, Armando.
Okay. So it seems like somebody was not, Eve was not able to hear me. I was wondering if Eve is able to hear now. All right, so I'll continue on. So the first thing is to split that set of strings, and how we would split it would be to we have the regular expression that would split. So this particular regular expression would split each word, and then because we want to match just words to words, actually, whether there is lowercase or uppercase, it doesn't matter. So we will use the Python function string.lower to make it all the strings into lowercase. So that initially is what you would do, and that's what let's examine the result of this particular function. So in this case, we have a quick brown fox jumps over the lazy dog. So if we run this particular one, we do, but notice that we get this extra space here. And actually, that is not a word that we're interested, right? So then one option to filter those particular words would be to then say, well, anything that for which the size is less than 0, just ignore it. And that's what this extra filter function. So this is a Python function, filter. So it's from the functional side of Python, or Python attempting to be functional. And what it's saying is take x and give it this particular function, and then x would be whatever argument or whatever array-like object you pass in on the as the second argument of this function. And that's why I added this filter elements that have length greater than 0. I'm sure you could find other ways to do the same sort of filtering, but this is one way, or you could do it also in the Python way, which would be something like return x for x in some list if length of x is greater than 0. That would be another way of doing the similar, that accomplishment similar. Oh, I think, is there a question? Nope, it seems so. That would be one way to accomplish something similar. So we run this now. Now we don't have that space there. And if we run our test, it should be all good. So the next one is to remove stop words. We did some of this when we were doing the previous lab. And the previous lab, we had Shakespeare's text. And we had sort of a mismatch of subwords of sort of modern English compared to Shakespeare's English. So yes, there was some mismatch there. But in this case, we do have some matching subwords compared to that will be useful to remove those that are inside our description. So, and how do you go about it? I think at this point you guys have done enough stop words or sort of filtering and whatnot, but I mean, somewhat similar to the previous function, where you can do it by doing a filter. And then what we want to do is, if that particular word is not in the stop words, then this will return true. This expression here, x at lower, not in stop words, and stop words is the set of stop words that we have already read in here. So this is an RDD, and we collect it. So if it is not in that collection, that will return true. And then this tokenize is the function that we wrote before that will give one word per would put each word as one element of an array. So when we're filtering the elements of this particular array. So that is one way of doing it. But notice that I also wrote here the previous way of doing the other way of doing it is sort of similar to what I explained before, that you sort of use this list comprehension from Python. So let's just run this. And so this is the list of stub words, and in this case, notice that we removed the, and that, yeah, actually that was the only stub word present in that particular sentence. Okay, so there is another. Oh, okay. So if you guys look in the chat, EL, recently just put another alternative way of doing the filtering. So I invite you to look it in there. All right. Any questions until here?
Yeah, Armando Aslam here.
Yes.
Can you run the test again for previous one and current one? Because I got one error for current one, so it will be helpful.
Okay, so you mean this one here?
Yeah.
This one? No, they all pass. And then the solution was this one here.
Yeah, but how we are handling the punctuations mark over here?
The punctuation marks, you want to remove those as well.
Yeah. Because one of the tests is to handle the punctuations, and I don't find how we are handling it.
We're handling when we do this regular expression.
The regular expression we have is not word. The capital W plus indicate like we are splitting with non-stop. Sorry, the punctuation mark. So ultimately, we are filtering that by using the backslash capital W plus.
Yes. Okay.
We are splitting like using the split regular expression, and we are taking backslash capital W that indicate non-word or non-printable character. You can say like the characters besides like 0 to 9, E to J, G, and underscore.
Yeah, that is the case. Right. Yeah, so I don't think, I think that would explain it. So that might be, and then what's the error were you getting?
What I was getting that my one of the tests which checks with the punctuation mark got failed. So that's why.
So have you used a small w or capital W?
Capital W, I think that's the
That is
given.
already written for you.
Yeah.
So the match is one character that is not a word character as defined by your engine.
Okay, let do it offline later.
Okay, sounds good. All right, so we remove all the words and tokenize the small set. So we have two small data sets for each ID. In the data set, tokenize the values and then count the number of tokens. So we have the tuple. We are building a tuple where the first element is the key, and the values are the tokenized version of the description. And so if we have that RDD, and we want to calculate the size or how many tokens there are in the full data set, we would be interested in mapping the second part, so all the tokens, and calculating the size of those tokens. And then if we want to sum over all of the tokens possible to then find out how many tokens we have in the full data set, then we will use the reduce function. And then in this particular case, we have we're saying how to do the reduction, and then we do the reduction by summing elements A and B. So at this point, A and B is just the length of the tokens, right? And that's what we will return. So in this case, we have we apply this count tokens RDD discount tokens to two RDDs, one from Amazon, the Amazon RDD, and one from the Google token RDD that we read over here. So we run that, we get that many tokens, and it all looks good. So one of the things that I mentioned in the previous session was to sometimes it's good to explore the content of the data. In this particular case, just because we've done many transformations. So in this case, this Amazon 2 token, which is the first one we calculated here. We have,
Armando?
yes, sir.
There's a question about somebody asked if we can do a flat map instead of the map. It is possible, but the problem is you're introducing a lot of unnecessary calculation, because what the flat map does is it will actually break your array and then create a new RDD with all the individual elements of the array. Since you just need to look at the length of this array, you don't need to do flat map. You can just do map, which is just a bit more performant in that case.
Oh, okay. Yes, that makes sense. Thank you, Ayo, for noticing. Yeah, absolutely. All right. Then, so I was saying, in this case, we look at the content of the data set and just to look at what we're processing, and that's exactly what we built. So the first element of the tuple is the unique ID, and then the second element is all the tokens. And these are the ones that we're going to then calculate the length of. So that is always good to just examine your data set. All right, so this is just to double check that everything was good, and in fact it is. And then this is, I guess, part of the exploratory analysis. Is good to know when you're gonna do all the sort of comparisons, what is sort of in the extremes of the distribution. So in this case, we're interested in finding out their record that has the most tokens. So at this point, you guys know how to do this for RDD. And for that, what we can do is we already have the RDD, and we would sort that particular RDD. We will sort that particular RDD by the length in reverse order, by the length of the list of tokens. And then because we only are interested in the record that has the most token, we only take one element. And if we were to run that, yeah, all looks good. So this is the particular record, and yeah, that passes the test. All right, so the next session introduces TF-IDF, which is a way of doing text similarity. Any questions related to TF-IDF? All right, no questions, good. So this particular one is a metric that would try to balance two things. For once, you want to measure you're measuring the term frequency. That what it does is just counts, as the name indicates, or counts frequencies or calculates the frequencies, tokens that appear many times in the same document, right? And then the other one, the IDF, so there are two terms to this metric. The IDF rewards tokens that are rare in the overall data set. And why is that useful? Is because it could be that there are tokens that appear often that might not be so meaningful for comparing two documents. But if a particular document has a rare term and another document also has that same rare term, maybe that is an indication that these two documents are close to each other. So in a way, you're balancing two things. You're balancing two metrics. So in the next one, I mean, and I think maybe the definition would come clear once we start doing the calculation.
Armando, I just people who wants to know more about any of machine learning or statistical data science, Wikipedia actually has great information on all of them. I just posted the wiki page for TF IDF, and basically the idea of the IDF is to filter out words that are prevalent and are there in many documents, and you say this is just noise. So you learn to ignore the noise and just look at the things that are actually unique.
Yes, absolutely. Yeah, I see. Sometimes they have a diagram that could be useful. I don't know. But yeah, that's a great resource. I'll make sure to add it to the notes. Would be a good idea. All right. So if we want to calculate the term frequency, so the first term in the TF-IDF, we would have a dictionary that the result, or what we want to get out of this particular function, is a dictionary of tokens and their term frequency, right? So what do we have to do? Well, we would have to count. And in this case, we're using Python dictionary. So initialize this particular dictionary. And the keys for that dictionary would be the tokens, right? So in this particular case, we check if that key is already part of this dictionary. What we would do? Well, we will increase the count of that key by 1. If the count is not in the dictionary, we will then add that key to the dictionary with the counter equal to 1. And at the end, we have the number of tokens, which is just the length of the tokens, the length of tokens. And why is that necessary? Is because if we're going to do the frequency in this particular case, the frequency will be the counts divided by the total length, or by the total number of tokens, right? That will give us the frequency of a particular token. And that's in fact what we do in the second part. So we're taking a dictionary that is counts, and we take the items of the dictionary. So this is going to be unpacked as a key value, where the key will be the token and the value will be the count. So the frequency associated to each one of those key will be therefore the value, which is the count that we calculated in the previous section, and the number of tokens, which is what we calculated in this particular line. And then we'll return this frequency, and notice again that this frequency is another Python dictionary, and that's what we want. Another way of doing it will be to use some sort of Python comprehension. So this is similar to list comprehension, and you would do what you would return would be this term, which is just the exact same frequency term here, and then we'll return a dictionary where the key is T, and then in this case T comes from counts, and counts is this other dictionary that we already filled up here with the counts for each token. So another alternative of doing it, I'm sure you guys might have seen another better. All right. Sounds good. Now, so I think there's another question on the chat, and I think this is just, would it be simply return? Yeah, yeah, is that exactly the same thing I put, or the thing I talk about dictionaries. Pre-calculate the length of tokens, so you don't need to do it for each token. I mean, the length you only go over once. This operation is only done once. This is not doing inside the for loop. So this particular operation you only do it once. So I think the question, I don't understand the particular question, because this is only run once when you call this function. All right. So if we run it in our test string, we'll get the frequency for each one of the terms, and then because they're each word only appears one, all the frequencies are the same, especially after removing the stop words. And if we go and test that, all the tests pass. Yeah, that's good. Now we create the corpus, and what a corpus is sort of like it is like the master data set, or the much larger data set. In this case, combining two smaller data sets. So in this particular case, our two data sets are the Amazon data set and the Google data set. And we combine them. And how do we combine them? Well, given that we have two RDDs, we can simply do the union of those two RDDs.
Armando, just a quick, just to let people know, people coming from SQL, union is a unique combination of tables, but in RDD, it's like a union all. So you don't actually filter duplicates when you do a union. It takes the entire first set and just appends the entire second set on the bottom.
Yes, thank you very much. Yes, very good point. That could be confusing sometimes. All right, and so if we were to examine the content of that, we will simply get what we would expect, which is the unique identifier and the set of tokens associated with that record. And that looks good. And if we were to test that, hopefully we'll pass. Yep. Now, if we want to implement the IDF function, let's see about it. So in this case, we have the corpus, and we're interested in calculating the IDF. So for each token, what we will return will be an RDD that would have the token and the IDF value. So if we want to count the number of tokens that we have, this particular would be calling the count function on the corpus. I think that is straightforward. And then if we want to calculate the unique tokens, in this case, we would have to do the flat map. And the reason for that is because we are doing it across the full data set, not on each record.
Armando,
Yes,
sorry,
sir.
The N is the actual number of IDs, not number of tokens.
Oh, yes,
Because,
yes.
corpus record is one record per ID. And because each ID contains all the tokens in a series, that's why you need to do the flat map to break that series in the second element of that RDD into individual words.
Correct. Yes. Yes, thank you. And then once we have those unique tokens, we would do the typical way of counting words, and that is mapping each word. In this case, we call tokens, to the number 1, and then we will reduce by key when summing the value. We would do it by summing each value 1 plus the other. And then, so if we want to do the inverse frequency of this particular token, so in this case, we're taking the token sum pair tuple that we would define here. So this particular tuple would have the token and the total count for that token in the corpus, right? And then here we calculate the inverse frequency of that particular token in the corpus by taking n, which is the number of records, divided by the frequency of that particular token in the corpus. And it's inverse because is not S1 over n, but n over S1. And so what this particular number would be for things that are very, very common would be larger, or it would be, it would be small actually. And then for things that are rare, this number would be larger, right? And so what that would do is things that are rare would have somewhat more importance in this inverse frequency metric. All right. Any questions until here? All good?
There was a question about do we need the float in the n? And the answer is yes, because count is an integer. And if you don't use the float and you do an n divided by something, it will become an integer instead of a float.
Yes. Right, yeah. You could do like, force it to do like this, but I find that is not so elegant and it's not so clear. So in this case, it's much more clear. Yeah, I agree. Thank you.
Armando, I have a question.
Yes.
Like for the unique tokens, I spent maybe 3-4 hours, to find that, and I try many things. And the question seems bit like the unique tokens. Here now we are calculating unique tokens based on the per row, you can say, right? Based on RDD, you can consider one particular row, and then we are finding the unique tokens in that particular row.
No, that's not what happens. The S1 actually represent the second element in the pair of the RDD.
That is correct. Like that is a list of words that you are getting there.
Yeah. So what the flat map, the unique tokens, what it does, let's go in line 10. So line 10 takes your full list. The RDD goes on the entire RDD. For each record, it blasts the second component into a list.
Right.
And what flat map does is at the end of this operation, it concatenates all those lists from each and every individual element into a new RDD. Okay.
Right.
So that's what the flat map actually does. So it takes the list from the first element. So let's say it was X1, 2, 3. It will create an X1, X2, X3, and then let's say the second one is Y with 4, 5, 6, and then it will append to the first one Y4, Y5, and Y6.
Right. So instead of that, if I use some other functions like values.
Yeah. So values, what values does is basically it's like a map of X and Y, return only the Y.
Yeah.
So values is identical to doing map S lambda S to S1. Okay?
Right.
So you don't expand it into individual items. The value at the end is still the entire list.
Right, exactly.
So but that's not what you need. You need to
Oh.
take that list and break it to individual words, so then you can distinct it.
So in this case, unique tokens, this is again the RDD, and it also has the ID itself, right?
Yes.
The token, I mean, the ID, like the ID that you get in Google Record and Amazon Record, right?
Yeah, no, so this unique tokens does not have the ID in it anymore, because the flat map doesn't return the ID. The flat map just returns the list of tokens in the IDD.
So my question is, if I use the values only, considering those the list elements, and if I use a distinct in that, then I'll get a distinct element out of the whole collection, you know.
No. So you will retain the key, right? So the map values retains the key.
Not map value. I'm using only values.
Okay, so values is just a map.
Right.
So, but you need to expand you didn't break the list into elements. So what you can do, if you do values and then flat map.
Yeah, that also it works. Yeah, I tried that also, and it works fine the way we have done here, the same way it works. But yeah, it took a lot of time. Like I try each and everything I searched in the Google, and ultimately like I came with this solution only. Thank you so much. It takes time. Thank you.
No worries.
Yeah, thank you. All right. All right, so now if we want to identify tokens with the smallest IDF, I think at this point you guys know how to do this one. Notice that because we're trying to get the smallest, we don't have to pass the minus, which we have done often when we're trying to get the greatest. So we're saying what to sort by, and in this case we're sorting by the second element of the tuple. All right. So what are the values with the smallest IDF? The smallest IDF. Yeah, so those are things that might not be so relevant when you compare documents. So I imagine that, yeah, we have new features, use software. That might not have so much information when you are trying to identify records that are different from each other. And we found this by actually just doing a calculation on the full corpus. So that is what this IDF brings to this metric. All right, and next is to do a histogram. So if we have a histogram of the IDF values, so in this case, what we would do is take those IDF values, which would be the second element of IDF small, right? Which is this tuple that we created in the previous cell. And what you would plot, it would be a histogram. So this is matplotlib of small IDF values. And if we were to run that and we run it in log scale, this is what we would get. We get that we have a lot of words. So in this particular case, it's a histogram. So the height, a higher bin means that that particular bin has higher frequency. So what that means is that most words would have an IDF of 400 plus. And then And then also notice that this is log scale. So then less words would be in this area here. All right. And you could do you could do the same using Apache Spark. Using Databricks, the Databricks interface. So in this case, we created a data frame from the small IDF RDD, and we create 2 columns. So this is how we would be mapping each one of those elements on each row of the RDD, and then we create a data frame from that. So
I have a question.
Yes.
Like how to decide the number of bins?
Okay, so how do you decide the number of bins? So I think the way I see it is an iterative process. So typically, what you would do is you would start with some fixed value. So I don't know, like 25 or a number, and then you see maybe if there are regions where the binning is coarse, or you realize that you have put you're then trying to identify what are the regions in your particular histogram that have high density. So if you want more resolution in that particular region, then you add more bins. And then if that doesn't help, you can do some sort of customized binning, where you would have maybe wider bins for the region where you have less data, and more bins in the regions that you have, wider bins where you have less data, and more bins where you have a lot of data. So that way will give you some sort of idea of the structure of the data where you have the structure of the data where you have a lot of data points, but then you won't lose and you know that you can somewhat separate that or split that area further because it's a high density region. But then in the low density area, if you were to do those super fine bins, and if there is no data, then that certainly is not going to tell you any information. So the way I see it is more of an iterative process. And then also, if you have some sort of inside information, say you're more interested in looking at the region between 100 and 150, then you might be able to do finer binning in that particular area. But it's, I think, a combination of data exploration and then whatever knowledge you might have. So if there's a business knowledge that you can incorporate there, you could include it. If somebody else has an idea or a suggestion of how to come up with binning, please share them with us. All right.
So while plotting the histogram, we can define the bin size, but I don't know about the Databricks display one.
Yeah, I don't think you can, but in Matplotlib that is straightforward. So there is so if we go back to it,
so the 50 here we are using as a bin.
Yes, exactly, right. So here is
you can define bins equal to yeah.
So we did that, but you could do something like 10, and then yeah, we see that maybe we want to explore something more in here in this area, or then this seems to be a high density region. Let's try to see if there is some sort of structure there that is hitting in the bins. And why that is the case is, let's say, if you have a bin that is low next to a bin that is high, and you combine them, the result would be somewhere in the middle, right? Well, this is log scale, so it might not necessarily be that case, but it would be somewhere in between these two lines, right? And then by splitting this, say, one wide bin into two bins, you saw some structure. So let's say we go to 20. We start seeing that something happened here. That actually this wide bin was only concentrated in this one part. Right, but what happens is if you keep splitting further and further, each one of those bins would have less statistics. And then you can actually pass a some, like, let's say, custom bins equals to some sort of array, which will be the bin edges. So let's just pass 50, 100, and then let's do a wide bin to 250, and then 500. Oh, I didn't put it in there, sorry. So this would be the bin edges, custom bins, right? Oh, so I think somebody was asking what is a bin. So a bin is in a history. So you have the x-axis in this case, and you split that x-axis into buckets, right? And each bucket, you count how many elements would fall within that one bucket or bin. And the size of that bin is either determined by putting size bins, so like we had before in the case that we have an integer, so like 10 or something like that. What it would do is would take the minimum value and the maximum value divided by 10, and then that particular operation would give you the size of the bin. So it would split in equal intervals the full axis. But you can also do customs where you define the edges. So notice that here, in this case, I put 0, 50, 100, 250, and 500. So what I'm saying is from 0 to 50, count how many records you have. And then the same thing from 50 to 100, and so on and so on. And that's what a bin is in terms of, or that's how you construct a histogram.
So Armando, I think this question is basically what is a histogram, and
yes,
people who don't understand it, a histogram shows you the distribution of your data between value ranges. So and the usage of a histogram for data science is to identify how the values in your column are distributed between the minimum and the maximum. So do you have like a normal distribution of values? Do you have a staggered or an off key? And it's a tool that's used by data science to understand what's the nature of the data they're dealing with. Where a lot of times you need to check, is your data distributed in a normal distribution, just to verify that the statistical analysis that you're doing on it makes sense. So a histogram gives you a quick way to see, are you a bell-shaped curve, which is a normal distribution, or something else?
Yes, exactly. Yeah. Yeah, so exactly, it calculates the frequency of occurrence, and then that in a way would give you an idea of the density of your data in that particular one dimension. So you could do histograms in 2 dimensions as well. But in this case, in the 1 dimension, you want to find those regions where all your data is accumulated, and then from that you can infer whether it is distributed as it was mentioned. It was distributed normal, or what sort of distribution it follows. Thank you for the clarification. Okay. All right. All right, so we can go through that. And then finally, we implement the TF-IDF. So remember that we already calculated the IDF. So the IDF used the full corpus to identify the inverse frequency. And the tokens are the tokens that are available in that particular inputs of tokens from Tokenize. All right, and the return would be a dictionary of the records and their TF-IDF value. So we already had the term frequency function that we define, and this particular function, remember, that returns a dictionary for each token would have their term frequency. So yes, so the term frequency in this case is the term frequency of that the term frequency of each word of that one record, right? While the IDF looks at the corpus as a whole, right? And so here what we're balancing is 2 things. We're balancing how often that particular record happens in this document versus how often it happens in the full data set. So that's what is called the corpus, the master or larger data set that we built by doing the union of the 2 data sets that we had. So if we already have a dictionary, so this TFs, remember, it has for each token the count, or sorry, the frequency. That is the first term of the the TF IDF, and then the second element would be the inverse frequency for that one token, right? And this is another dictionary, and how we access the dictionary is by passing the key. In this case, the key is the token. And what are we interested in building? We're interested in building another dictionary that would contain the TF-IDF. So we calculate the first element, multiply by the second element for all those tokens that are in the tokens list. And so in here we pass this particular record, right? And how do we get this particular record? Well, we have the Amazon RDD, and we filter that particular RDD by matching those records for which the first element is equal to this particular string. And in this case, there's only 1. And we would collect that and take the
the first
element
is for the first record.
Yes.
And 1 is the second element in the first record.
The second, yes, exactly, which is the list of tokens for that record, right? And that's what this TF-IDF we built is expecting. And right, okay. So we run that. We get this, sorry.
So just a quick comment here about, people were doing the work and saying, hey, we got a lot of crazy Spark errors when we were trying to run the things. And doing something like that helps you debug your functions. So if you do, instead of collect, use take 1, 0, and 1, and that will give you the element of the row that you need to pass. And if you just test your function with one row, you will get an error that you can see and identify what the problem is, and not some cryptic Spark error or something broke up in stage 5, task 4.
Yes, I agree. Very useful to know what your transformations are doing or whatever operations you're doing on your RDD. So yes, examining your data sets are always the way to go, or to at least ensure that whatever you're doing or you think you're doing is actually happening. Thank you. Okay, so we're almost done. Oh no, we still have some way to go, sorry. All right, the next thing is, well, if you have a vector, or you can see this this TF-IDF as a vector, right? Where the coordinate of the vector would be, say in this case, the token, and the value of that dimension will be the TF-IDF, right? So in principle, if I have this one vector and this other vector here, and I want to compare them, well, if this word is present here in this record and this record, and then this other word is also present and a few other words are present, well, that might be an indication that there is some intersection, and therefore those two records might be similar. But also we have to take into account the value of each one of those dimensions. And that's what we'll do in the next session, trying to find ways to measure the similarity between two records, right? So the first similarity that we're implementing is the cosine similarity. And to get there, well, the cosine similarity is defined as the dot product of A and B, so vector A and vector B, divided by the norm of A and the norm of B. And the norm of A is the sum of the sum of each one of the elements square and then the square root. So this is the Euclidean norm of that vector. And here we have the dot product, which is defined as each one of the elements, or so element I of vector 1 times element I of vector B, and then sum that over all i's. So in this case, I is the number of dimensions, which in this case would be the number of unique tokens that are in the full corpus. What if I and B are of different lengths? So if I and B are of different lengths, you would not be able to calculate the dot product. I mean, it will be undefined because notice that in this case, A and B, sorry, are of the same dimension. In this case, the dimension of the vector is the number of tokens in the full corpus. So if we look back to the to what a vector looks like, right? It's something like this. So we have token and a value associated with that token. So you would think, oh, wait a minute, A, the dimension of A is just simply the number of tokens that you have here. But actually, that is not the case. What happens is that all the other tokens for which we don't have a value, or at least we don't see it here, their value is 0, right? So for this particular exercise, all the vectors have the same dimension. And when we're calculating the dot product, what we're multiplying is if there is a match. So if this, in this case, the word AutoCAD is present in this vector and in on the B vector, which let's say is here, then you will multiply those two values. If it is not present, well, it's the same. You don't multiply, which is the same as multiply by 0 in the other element. Okay, so there was a question. There is a comment on the chat saying that the dimension of the vectors in this case is effectively only the tokens that the two records have in common. So therefore, they will be by definition the same length. Exactly. Yeah. That is what happens when you only multiply the intersection of the tokens. All right. So the first thing would be to then define that that dot product, right? So if we have two vectors, A and B, we have yes, actually that makes me think this is a very good point, because we're not going over the full corpus, right? But what we're doing is only taking the elements that are in the vector A that are also in the vector B. And if that is the case, we will multiply the values of A by the values of B of that particular token. So somebody's suggesting that in your solution, the order of A and B matters. No, it's just counting if, I think you made another comment now. But yeah, it's just actually looking, if it is in A, go and see if it is in B. But in this case, the order of the tokens is not relevant.
Yeah, and I think, Armando, you mentioned a point that you kind of glanced over about the sizes. And what you do in data science is you have sparse matrices.
Mm-hmm.
And what you're doing is saying, I'm basically creating a matrix with the combined words in both elements, where everything that's missing in A will be assigned a number 0. And that's why it allows you to just ignore it and just filter the ones that are in both, just because of the nature of your actual calculation.
Correct.
But if the calculation was different, then you may not have done that.
Exactly. Yes. Yeah. Exactly. This particular dot product, that's what it does. So yeah, thank you for the comment. Yeah. So yeah, effectively, this is our sparse. This particular data is very sparse, because for each record we only have values on some of the tokens, not and that fraction compared to the full corpus would be small. So yes, very sparse data. And then, so if we want to take the norm of one of the vectors, well, we already defined the dot product. Why not use it, right? So the dot product of A with A would be the norm square. And then we take the square root and we get the norm. And then the cosine similarity, well, from our definition, is the dot product of A and B divided by the norm of A and the norm of B. You could rewrite this, I guess, put in the parentheses, but they're both equivalent. And so yes, we have here two test vectors, and if we were to run that, we get some values. But let's do the following just to add some off. And let's just for fun. Let's add another element here. Hello. Oh, 5, 10. Yeah, it didn't break the calculation. That's good. Why is that? Yes, because in our dot product definition, we only take those elements that are common. So then this hello would not pass that. But effectively would be the same as if we would have here hello of value 0. Right? We get the same value, yes. So imagine that for all the other dimensions, you have zeros. That is exactly the same as just multiplying the ones that are in the intersection of the two vectors, or the two sets, two keys. Okay. Oh, this is gonna fail now, hopefully. Oh no, it will not fail. Yeah, it failed because we changed we added this one vector. So if we rerun there, we can leave it there. We can leave it there just for time. I'll make sure I change it when I send the solution to everyone. All right, now we want to implement that cosine similarity between string 1 and string 2, and the third element, or the third argument for this function is the IDF dictionary that will have the IDF metric for all tokens. And how will we go about it? Well, we first have to tokenize the string 1. So tokenize is something that we define early on, and I would split this particular string into words, and we will calculate the TF IDF of that particular list of tokens, right? And to calculate the TF IDF, you need the IDF in the corpus, which is why we pass this dictionary here. And this TF IDF, we already defined it. And since we already sort of built all the helper functions up to this point, we just have to actually just call them. So that's why in the first one we called the TF-IDF, the second one same for the second string, and then the cosine similarity between these two dictionaries. So at this point we build the dictionary, the TF, or we move this one string, the simple string, into the space of the corpus, and meaning that we have the TF IDF for each one of the tokens of that string, and we just call the cosine similarity that we defined earlier. And so if we were to run this, that's what we get. Any questions until here? I think there was some. I think in the forum there were some people having some issues with what this particular cosine similarity function. So if the question's still up, maybe comment. Speak up now so we can go over. Maybe trying to understand what was happening there. Otherwise, we will continue on. All right. So the next thing we do is we actually implement the entity resolution. And what that means is that for every record in this small data set, we will use the cosine similarity to compute a similarity to every record on the Amazon dataset. So notice that this is very expensive because we are comparing each record to each record on the other dataset. Right? So imagine that you have millions of records, which is typical of this sort of big data sets. You would do a lot of unnecessary computations. So something to think about, and we address that in the next session, sections. Yes. So the steps to perform would be to first create an RDD that is a combination of the two data sets, right? And a function that, given an element from the combination, computes the cosine similarity for the two records in the element. All right. So what is this cross? So it's suggesting to use the Cartesian method. So you can always go back to it. Go to the documentation. Oh, actually, this is pointing to the 1.62, but it should be the same. Maybe returns the Cartesian product of one RDD with the other. So, and what that means is that takes all the pair of elements A and B, where A is the elements of the first RDD and B are the elements of the second RDD. And why is that why is that useful in this particular case is since we're going to do a comparison of each record to all the elements on the other record, we would like to know, we would like to sort of create this data structure that would help doing that comparison. Right? So imagine what this Cartesian product is doing is for each row of this data set, it would sort of copy all the rows of the second data set. So first row, all the elements of the second data set. Second row, all the elements of the second data set, and so on and so on. Then we will look at we look to calculate the compute similarity function, which will take one of those records, right? So a record is a pair that would contain a Google record and an Amazon record, and will return a pair, which would be the Google URL, the Amazon ID, and the similarity between those two. So given that construction, the first record would be the Google record, right? The second would be, so the second element would be the Amazon record. The URL, why would we need that? Well, because that is what we are going to output, would be the first element of the Google record, and the Amazon ID would be the first element of the Amazon record. And the value would be the second element. So all good until there. And since we already have what we need to get our output, right? We have the Google URL, the Amazon ID that we extracted. And then we need to calculate the cosine similarity. Well, how do we do that? We do it by passing the two strings. So this is the Google value. Okay, which is the Google value, the Amazon value, and then the dictionary with the IDs, with the IDFs for this particular data set, right? So one thing is that here we're not going over the full data set. This is a smaller sample. And why we do that is because you can, in principle, do this with a much larger data set, but then you will be doing a lot of computation. computations. And that's what, so this is what would happen, right? So if we calculate the similarity between record A and record B, this particular similar function will return the similarity, which in turn would call this compute similarity function that we define above. Any questions until here? All right, we are well past 8 p.m., but I'll continue a little bit more. So this solution works well for a small data set, but requires Spark to send the IDF small weights, which is our dictionary with the TF IDFs, to all the workers for each record. For example, if we only have one worker, then, and we have 1,000 records, we will be sending this particular variable, right, to the same worker 1,000 times. And also we didn't cache it. So what we can do is actually tell the worker or tell the driver to copy that IDF small weights to the worker. So then we won't have to we would have to be reading that from the disk or recreating that particular RED. And that's what broadcast does. So we looked at broadcast in the previous the previous session. So if you do have questions, you could jump in now. Otherwise, I will go into the compute similarity with broadcast. So the first function that looks identical, right? The only difference is that in this case, we are broadcasting this particular IDF small weights to all the workers, so they won't have to request it. And why do we do that? Because notice that for each record, for each comparison, right, for each cosine similarity that we're calculating, we are passing that variable, right? So if we know that we're going to be doing that, and this particular data set is small, it would be a good idea to do a broadcast, so you don't have to repeat or do this operation, or you're doing the same operation, but at least you're doing it in a more efficient manner. And then the rest is just the same. So therefore, the calculation should be identical. Any questions until here?
Armando, just a quick comment about broadcast, so people know when you broadcast an element, it stays there forever. It's not there just for your current operation. You can reuse it for multiple operations, but it will keep on taking that memory on the executor even if you stopped using it. So when you're done with an element, either unpersist it or destroy it to release that memory. Otherwise, you have a chunk of memory on the executors that is stored for, this could be a, even a meg or 2 megs of information for big files that right now is held up with just garbage. So that's just for information.
Thank you. That's very useful. Actually, but this is per job, right? Like after the job dies, that would be collected.
It's per SC.
Oh, it's so, SC.
Yeah. So it continues for multiple jobs.
Ah.
Yeah. So it stays there until you tell it, I'm done.
Okay, then yes, you better free up that memory because it could add up quickly.
Yeah, exactly. If it's a large, if it's a small object, you know, only small, a few Ks, doesn't matter. But if you send something significant and then you say, hey, I've finished using it, just clean it up.
Yeah, that makes sense. Thank you.
And there was a quick question, what is a worker function? The worker function is where Spark actually executes the command. So the master is where the command is distributed from, and the worker is the individual nodes where the RDD actually is, and that's where the activity actually takes place. That's the distributed calculation.
Yeah, thank you. All right, so in this particular case, we do have a file that would be the master file that would tell us if two records are actually equal to each other, or what is the similarity between the two records. Yes. So well, the first thing to do is to read that actual file. I don't think there was anything here to be written, but remember, always good idea to examine what that particular data set would look like. So if we add cell above, and then we do something like take 5. All right. So it would have the Amazon record, the Google record, and then gold. What? So it's a tuple of 3 elements, right? Oh, no, I'm confused. Okay, so the pair would be, okay, 1 if successful and 0 otherwise. So gold 0, 1 would tell us if the actual two records are the same or not. So, well, we can do a lot of operations with this gold standard. For instance, how many true duplicate pair are between the two data set? What is the average similarity? What about non-duplicates, etc. So I'm sure you guys read this part, so let's get into the actual calculations. So we had similarities broadcast, right? We had that, where do we have that? That was what we calculated in the previous section. Right here, oops. I don't know why my browser is lagging a little bit. But that is this data set that we calculated here. Sorry, it's a bit too slow. Okay. So what we are calculating is the sims. Create a new RDD sims for the RDD similarities broadcast, where each element consists of a pair, Amazon ID, Google ID, and cosine similarity. And that's what we're doing here. We're building this tuple that would contain the Amazon ID, the Google URL, and the cosine similarity score. And this is from this other data, or from this other RED that we already had calculated. And then the next thing to do would be to then join that data set, that similarity data set, with the gold standard data set. And, oh, sorry, I can't remember what this is. Let's think about it. Similarity, let me just run this for a second. I forgot what I did here. Okay, for this run. So let's take a look at what Sims does. That's Sims take 5. Okay, in the meantime, I'm gonna post the link for the attendance this week. So I'll post it on the chat and also on the oops, sorry. And then I posted also on the Slack channel. Here is so let's see, hopefully it's working. Yeah.
Hey, sorry to interrupt.
Yes.
I think attendance link shows like attendance week 3. Do we need something?
Oh, yeah, that is actually a good point. Yeah, it is 4. So this. Yeah, so if you feel that is fine.
Okay.
Yeah, it was a typo because it was a copy from the previous week. So that's why it shows the wrong number. But thank you for noticing. So gold standard. James John gold standard. Okay, yes. And add cell below. All right. And then this mapping here, what we do is take the second element of this tuple, and then okay. So what is happening here? I got back to it. So join would only there would be a left join. So only those elements that are in the Sims RDD and in the gold standard RDD would have value. And this particular join, if you see the result, would be the tuple that we created, right? That would have the 2 records. The first element would have the similarity, and sorry, the second element would be the tuple, where the first element is the similarity, and the second element is just a gold saying that yes, those are duplicates. So that's why after doing the join, only those elements will survive. And if we therefore do the count of those elements, that would result on only showing us the true duplicates elements, the true duplicate between the two data sets. So if we have that count already, we have the true duplicates, we could then calculate the average similarity for those duplicates. And how would we do that? Well, we would take the similarity between the similarity for this true duplicates, right? And remember that in this true duplicates, we only had the similarity value. So we don't have to do maps or anything like that. Directly what we do is reduce that particular RDD. And in this reduce, what it's doing is just summing all the elements of this RDD. And we divide by the count to get the average similarity. And why is that useful? Is because you could then, if you know that a true element, the similarity is a number, whatever the number it is, let's say a 0.2 or whatever number. If you know that a true duplicate would have a similarity of 0.2, then you could say, well, if any comparison that I do going forward, their similarity is greater than 0.2, then I'm going to say that that is similar. That could be your way of tuning or setting the threshold for filtering similar records. And then if we want to look at the non-duplicate, would be, and in this case, we'd do, instead of a left join, would do a left outer join. And then what this would do is do the join even for elements, do the join of sims with gold standard, even for those elements that don't match, right? As opposed to this one where we only do where the key matches, right? For the two RDDs.
Armando, I
Yes,
think
sir.
the join will do the inner join, not left join, I guess.
Let me
Yeah.
think about it.
That is correct. The join is
Yes.
an inner join, and
Yes.
the left outer is a left outer.
Yes, thank you. Thank you for noticing. Yes, inner join. So it would be only those elements that are in both RDDs. Correct. Thank you. And then we'll filter those that that have similarity, or that have gold standard equal none, right? Meaning that there was no match. And then we will take the similarity. So the second element, so that is that index 1, correspond to that tuple, this particular tuple here, that would be the similarity and the string gold. And then we do some sort of similar operation to calculate the average similarity. So here you see that the average similarity for true duplicates is 0.26, blah, blah, blah. And for non-duplicates is 0.001234. So, but this is just 1 point estimate. I think what I would do would be, if I wanted to actually truly see what is the distribution of this data, what you could do is send a histogram of all the similarities for the non-duplicates, a histogram for the similarity of all the duplicates, right? And we know that the average would be somewhere in between, so you would have two distributions. Maybe one distribution here, how am I drawing here? Compared to histograms. Let's see if Google would have some nice images of that. All right, let's look at this one here. So let's say that the non-duplicates would be some sort of distribution like this, and the one of duplicates would be a blue distribution like this. And then, the mean in this case we saw it was 0.2, and then for the other one the mean was 0.0. And then you would decide somewhere in between this mean and this mean where you would cut, right? And then notice that there will be some contamination, meaning that some of the blue data would be on the left side of this particular cut. If, say, I decide to select the cut to be here, or vice versa, anything to the right of that particular cut, there will be some red and some blue. And how would you choose that? Then that's how you would know that there will be some true positives, some false negatives, some true positives, some true negatives, and then some false negatives and false positives, meaning that were identified that were not identified correctly. All right, I think we're well past our 8 p.m. cut. So for the next session, I will just post the solutions, but then feel free to comment out. I think one thing I would say, we did a lot of comparisons here, but that is not the smart way of doing it. And the next part of the lab, that's what precisely you would explore. So unless somebody has any other questions, we'll leave it like this for today. I will send the solutions for this lab later on, actually tomorrow, when I release also the materials for the next week, where we will start getting more into machine learning. And that will be the next 4 sessions, more focused on the machine learning part. Although this lab today, what we did is very much related to machine learning or data science, whatever you want to call it. That is the sort of operation that you would have to do when you're dealing with text data. Any questions until here, or we can leave it there?
Yeah, so Aslam, so
Yeah.
for this exercise I don't get completed, so what I should do now? So I should publish the half complete notebook to you?
If you want to work a little bit more into it, that's fine. Feel free, and then submit it before end of day today, or sometime tomorrow, but probably not before I send the solution. No.
Okay, and one more question, like in this we have auto graders in the end or something.
Ignore that. That was a mistake on my part. So these labs are based on the labs done in a course in the EDX platform that Databricks was teaching. Unfortunately, when I was preparing the notebook, I missed to remove that part. So just ignore it for now. You don't have to do auto grader. You just have to submit the notebook, the link to it. Yeah.
Okay.
Armando, just before we leave, I just wanted to stress the point of validating your result against true and false, and how important that is in data science. And you would definitely investigate what you have a bit more, and you will use that information to improve your model in an iterative way. So your false negatives and false positives are reduced.
Right. Yeah. Absolutely. Yeah. I typically spend a lot of time doing plots, so histograms is my go-to plot, and that would give me some idea of what's happening. But yeah, I agree with you. Always make sure that you are critical, or like you are constantly checking that the work you're doing makes sense. By not only just apply algorithms and then just hope for the best, but actually understand